Good morning to all. Today we will continue the same topic, that is floating point number representation. And during representation of floating point number representation, what was the key observation? For representing number, we should have a word, that word consists of mantissa and the exponent, mantissa and okay. So, that is we have seen, and then we have seen the example also one. And another very important message is last class we discussed, that is representation of 0. Okay. For representing 0, we have two problems, or we have two thoughts. Okay. So, first one is how do you represent the 0. So, in that first thought we said ki okay. So, first thought was, so maybe topic we can give issues in 0 representation. So, obviously mantissa part must be 0. So, there is no doubt that m should be 0. Okay. Now, so let us say what we do it, number we can write n equal to, so mantissa into 2 to the power e, okay, that is we write. So, what we are saying, this should be 0, that is no doubt, and this value will be 0 if m is 0 and e can have any values. Okay. As I said in the last class, so why do you represent, why do you waste the different combination of e for representing 0. So, therefore, what we concluded that number 0 should be, if this is mantissa and this is exponent, we should have 0 here, that is no doubt, but exponent part should have a largest representable negative number. Why do you so? Why do I do that one, or why it is done? Because let us say one number is 0.001 into 2 to the power let us say 3. If mantissa is only 2 bits, so that means only this one. So, then we can say this number is 0 irrespective of this value of exponent, but if I normalize it, so then what will be the value? 0.01 into 2 to the power 4, 0.10 into 2 to the power 3. That means, this number is not actually 0, this is not 0, because here we have the value 0.10 into 2 to the power 3. So, best way to represent the number is when this value will be highest representable negative number. Let us say if you have the exponent part, you have 3 bits. Okay. So, then what will be the highest representable number, negative number? We want to represent the number positive as well as negative number. Then what do you find it here? Say, okay, let me explain it in details here. 3 bits. So, 3 bits number, what are the combination using 3 bits? So, we have combination, it can be 0 0 0, it can be 0 0 1, it can be 0 1 0, it can be 0 1 1, it can be 1 0 0, it can be 1 0 1, 1 1 0, and 1 1 1. So, we have total 8 combination. Okay. So, using 8 combination we can represent the number. If it is 0, either we can represent the number -4 to +3, or we can represent the number -3 to +4, because we have total 8 combination. Using 8 combination we can represent 8 numbers. Okay. So, therefore, what will be the highest negative number? Highest negative number will be either -4 or -3, because see, you can say this one is, this one you can say this is -4, or this one you can say +4. In that case, highest negative number will be -3. So, anyway, that highest negative number in this case will be, highest negative number, if I write k, will be 2 to the power number of bit for exponent, let us say 2 to the power what is that, 2 to the power k okay, sorry, 2 to the power k minus 1, highest negative number, it can be this one, or highest capital K is equal to 2 to the power k minus 1 plus 1. Okay. So, therefore, best way to represent the negative number is matrices should be 0 and exponent should be highest negative number. Okay. So, then highest negative number in earlier example what will happen? So, this will be the highest negative number. So, earlier example we put 0.00, let us say 0.001 into 2 to the power highest negative number is -4. Now, if you go for normalization, so there will be underflow. So, in that case say we can say using this, this means with mantissa 2 bits and exponent 3 bits, we can represent the highest, we can represent the values here. In that case 0, this value will be very close to 0, because this is 0, you cannot again normalize it. So, if you put 0.01, this will be 2 to the power -5. So, you cannot represent using 3 bits. So, therefore, this one thought is saying you represent the number mantissa will be 0 and then exponent will be highest negative number. Another thought is saying ki 0 must be represented as sequence of zeros. That means 0, second thought says ki this should be 0 0 0, not only that exponent also should be 0. Okay. So, this is this should be also, so this should be also 0. But one thought is it should be negative number, then another is saying is 0 0 0. So, to match this one, what is done is whatever the desired number, desired exponent, so we add that value with the highest negative number, okay, while representing the exponent. In other way around, how do you get 0? We have represented minus k and this is 0. So, what we do it? You add k, then this number will be 0 0 0. So, in summary, what we do it? If we want to represent a number, we identify what is the desired exponent. So, desired exponent means what should be the exponent value? Let us say 1.15 or let us say 1.75. So, how do you represent 1.11 and exponent is 2 to the power 3, let us say. So, 3 is actual. So, now when you represent in floating point representation, what we do it? We will add 1.11 into 2 to the power 3 plus k, k is the highest magnitude of the highest negative number. Now, while we do any kind of operation, what we do it? 1 1 into 2 to the power 3 k minus k. So, we add the k value and then while doing some computation we subtract it. So, that is the way it is represented. Okay. So, therefore, this will be this condition is also satisfied, this condition is also satisfied. Okay. So, therefore, this representation whatever the value we are representing into excess k representation. So, therefore, this representation is called the excess k code, k is nothing but the highest representable number and this value k is called the bias and this entire representation is called the bias exponent. So, this entire representation is called bias exponent representation for exponent. Okay. Okay. So, we learned that in this scenario what we should do, best way to represent the number exponent is in the bias exponent. One another advantage is that bias no need to write whether it is a positive or negative. So, bias will be represented only the positive number, because whenever we require it we will subtract the value of k. Okay. So, now what we do it in next we will learn having this concept with us, what we do it we will know actually how the number is represented in computer system. So, here what we do it, there is a some standard. So, that is some standard is something called IEEE754 format. Okay. So, this representation is something called IEEE 754 floating point format for representing floating point number. So, number 1 is IEEE 754 format, they use the bias exponent. Okay. So, they use the bias exponent. Then bias exponent is how many bits, that we need to check. So, in floating point number representation is actually 32 bit, entire floating point number will be represented in 32 bits. So, this will be what do you write it, this is sign bit, this will be 1 bit and then this is exponent, this will be 8 bit, this is 8 bit and rest is 23 bit is mantissa. Okay, total is 32 bits. So, mantissa is always normalized. When you represent the number should be normalized form. So, mantissa is always normalized, that means we can assume that if entire part this is the mantissa. So, before the mantissa there should be a dot. Okay. So, if the number is let us say in mantissa is 1 1 0 0 0. So, 21 0 and then 1, total 23 bits. So, this should be like that. Here is one interesting thing, what is that? So, it is assumed that before mantissa there is one implicit 1, there is one implicit 1. So, therefore, actually mantissa is 23 bit, but while number is represented it is actually in 24 bits, because 1 we are not representing, but we are assuming that 1 is there. So, therefore, precision is increased by 1 bit. Okay. So, whatever the number will be there, we will assume before the left side there should be 1. So, there should be 1 point whatever the number is. Okay. So, therefore, in exponent this IEEE 75 format. So, entire number is represented is something like what will be the value of n number. So, it will be minus 1 and whatever is the value or s, that is sign. If it is 0, that means this will be 0. So, it is a positive number, and if s is 1, so this value will be minus 1. So, that will be, it is a negative number. So, minus 1 into then mantissa. Mantissa is m. So, let us say this is the mantissa m and this is exponent. Whatever the mantissa value, so it should be 1 into mantissa, 1 point, not into 1 point mantissa multiplied into exponent, that is 2 to the power, that is base. This is, as we learned, this is mantissa and this is exponent. Exponent will be 2 to the power, whatever the exponent value, minus 127. So, here because of the, we have 8 bits exponent. So, therefore, how many combination we will have? 2 to the power 56 combination. Okay. Out of this 256 combination, so 0 and 255 combination are reserves. So, rest are used to represent the normalized number. So, for any value this will be valid when 0 is 255. Okay. And this is bias exponent, and this is something called 127 XS code, that is also said. That means, if you want to represent any number, so in the exponent part we have to add 127 and then we represent it into the computer system. Similarly, when we do some operation, so if you take out the number here, then what you have to do? We have to subtract the value of the exponent and then we do the operation. Okay. So, then what is the advantage? So, because while representing it should be minus k, that is we learn it, and then while doing some operation, as I said, is during comparison this will be very useful. So, therefore, that time we should see that all 0 is nothing but the all sequence of 0. Okay. So, this is the representation. Here we will study more in details. Say, let us say, this is the value for a normalized number. Now, what will be the highest representable number? What will be the highest representable table? Let us say positive number. Okay. Okay. Okay, highest representable positive number. Again you consider the diagram earlier here. So, we have a sign bit here, we have exponent, how many bits? 8 bits, okay, 8, and then mantissa will have 23 bits, and we will assume this is 1 point this mantissa. Okay. So, then what will be the value? Highest value will be E, that is exponent should have the highest value. What will be the highest value? It has 8 bits. So, 0 to 255, but as I said 0 and 255 are reserves. So, therefore, exponent will have the highest value is all 1. Okay. And then positive number means this should be 0, and mantissa, when will be the highest value? All are 1, say 23. 1. So, then what will be the value? So, value will be, as I said, ki minus 1 into s, s is what? S is 0 into 1 into mantissa, 1 point mantissa, mantissa is all 1. Okay. So, 1 into mantissa, where m is all 1 into 2 to the power e minus, what is this value? This is 255, but 255 is reserved. So, this will be 254. So, E should be, say this is the value we learn it. So, highest value will be, so this will be 0, that means 1 into 1.231 into 2 to the power highest value, this will be E minus highest, this will be 254 minus 127. So, this will be 127. Okay. So, if you compute it, this is nothing but 2 minus 2 to the power minus 23 into 2 to the power 127. How are you getting this one? So, let us say what is the value of 1.11? 1.11 is, we can write it 2 minus 2 to the power 4. How many ones? That is 2 ones. So, how minus 2 to the power 2, sorry 2 to the power 2. So, what is this value? This will be 1.75, right. So, this is 2 minus 1 by 4. So, this is also 1.75. Similarly, what will be the value of 1.111? This will be 2 minus 1 by 8. So, therefore, 1.11231 is nothing but this value into 2 to the power 127. So, this is equivalent to decimal value is 3.40 into 10 to the power 38. So, therefore, using 32 bits we can represent highest representable number is this value. And what will be the least positive number? Least positive number means mantissa will be, it should be normalized. So, mantissa will be all 0. So, therefore, so if you represent it least positive number, this sign bit should be 0, and least exponent. Exponent, what is the exponent value is e minus 127, where E is ranging greater than 0, greater than 127, sorry 255. So, 255. Okay. So, therefore, what will be the number? Least number will be 1. So, this should be 1. So, this is 0 0 0 0, this should be 1, okay. And this should be what? All 0, least value, say it can be all 0. So, what will be the value if you put in a formula here? So, this will be 1. So, if you put a formula, what will get it? This will be 1 into 1 point all 0. So, it is only 1 into 2 to the power E. What is the value of E? 1 minus 127. So, E 2 to the power minus 126. This is the least value, this is least positive number. Okay. So, this will be close to the number 1.18 into 10 to the power minus 38. This is positive, this is 10 to the power minus 38. This is the highest, sorry, the least positive number, and the highest positive number as we calculated this one. Okay. Now, what we do it? We will check out how we should represent the number. Say one example here. Okay. Let us say we want to represent the number 3.25 in IEEE 754 32 bit represent 32 bit format. So, it is a positive number. First task is you have to convert this number into corresponding binary. So, this binary will be this one. So, this number can be written as 0 1 into 2 to the power 0, no doubt. Now, you have to normalize the number. You have to normalize in such a way 1 point something, because 1 is implicit. So, 1 is implicit, yeah. So, then what you do? You can do it 1.101 into 2 to the power 1. So, 1 will be implicit, this part will go in mantissa and this part will go in exponent. So, therefore, so number we can represent in IEEE 754 format. This is a positive number. So, this sign bit and exponent is 1, right. 1 means this is the actual value is 1. So, therefore, when we represent the number into 754 format, you want to store the number, then what you have to? You have to add 127. So, this should be exponent should have contain 128. Okay. So, therefore, 1 0 0 0 0 0 0 0 0 0. So, this will be all 0, okay. And then mantissa will be 101, that means 1 is implicit. So, therefore, number will be 1.101 into 2 to the power 1 plus 127. If it is negative, so this will be minus. Okay. So, this is the way if you want to represent floating point number, sorry, decimal number to corresponding binary number in 754 format. Okay. So, we will see one more example. Let us say we have a number, okay, I can go next page, yeah. So, suppose we have a number a, so this is sign bit and then we have the exponent is 0 0 1 0, then 1 1 1 1 1 2 3 4 5 6 7 8, okay. And then mantissa is only 1, rest all 0. So, this is total 23 bit, this is 8 bits. This is mantissa, sorry, this is exponent. So, this is exponent and this is mantissa. Okay. So, what will be the corresponding decimal value of this number? So, we know the also called value here is minus 1 into s into 1 point m, whatever the mantissa value, into 2 to the power e minus 127. So, this is the value. So, now this is already represented number, okay. So, that is the number. So, what you have to do? We have to get the actual, you have to subtract the exponent. Earlier we were adding, now we have to subtract the exponent. So, therefore, we have to find what is this value actually, and this is a negative number, okay. So, how do you get? This is 1, 2 to the power 0, this is 2, this will be 4, this will be 8, this will be 16, this will be 32. So, the number that is exponent is nothing but 32 plus 8, so what is 40, 40 plus 4, 44 plus 2, 46 plus 1, 47. So, exponent is actually 47. So, what is the actual exponent? So, actual exponent is E, that is 47 minus 127. So, how much it will come? Minus 80. Okay. So, therefore, and what is this value? 0.1 is nothing but 0.5, right. So, therefore, number is nothing but minus 1.5 into 2 to the power minus 80. This is equivalent the number. Yeah. Okay. So, I will end this talk with a note, that is something called is the special representation for number. Similarly, there is something called 64-bit representation. So, that time sign bit always will be 1, exponent will be 11-bit and next 52-bit will be for, okay, I can write it here. So, this is something called double precision. So, this is 64-bit. So, this will be 1, this will be 11 and 52, this will be mantissa, this will be exponent, and obviously we know this will be the sign bit. So, this is one representation, that time number, that formula will change, and this is something excess, that is 1023 excess. So, because 11, okay, 11 means what? 2 to the power 11 minus 1. So, this will be 2 to the power 10, 10 means 2 to the power 10 means 2024, and then you have to reserve 1. So, therefore, excess 102, either 1024 or 1023. So, excess 1023. Okay. So, now we come back the, that is 32-bit representation, we have few cases. Okay. So, when we will say this number is 0, and then when there is underflow and overflow indication bit. So, here if m is 0 and exponent is highest negative number means what? So, you add highest negative number is minus k, right, and you add plus k. So, then it will be 0. So, e will be 0. So, then we will say this number is 0. If m not equal to 0, however, exponent becomes 0, that means you cannot further normalize it. So, this indicate the underflow. Okay. And there is something, this is 0 or exponent is actually 255, that means you cannot further increase the exponent. Okay. So, that indicates the overflow. And then last one is m is not equal to 0 and e also not equal to 255. So, that is represent not a number, means this happen when you do divided by 0 or something. Okay. So, with this note I end today's class, that is IEEE754 format. So, typically in exam we ask what will be the corresponding value of this representation, as I have already shown one example. Maybe I can tell you one more example here. So, let us say if b is a number and then 1 0 0 0 1 1 1 0 and then number is 0 0 0 0 0 0 last to what will be the corresponding decimal value, or you represent number 1.5 into IEEE754 format. So, this type of question may be asked in exam, or you should know how that if the number is decimal, how do you represent into corresponding IEEE754 format, or if number is already in IEEE754 format, how do you convert to corresponding decimal value. Okay. I stop here.